I hope that you guys are having a great day, great start to your day. I hope that everyone, drank their coffee and took their vitamins and all that good stuff. Today, we are going to be turning the page on some of the content that we've talked about. I wanted to also give you a little bit of an update. I mentioned this in my announcement. I don't know if everyone's had the time to read that quite yet, but Friday will be an asynchronous meeting, so I will have a recording of that class available for you before class on Friday or that class time. So just hang out for that. Second item is your exam grades are not yet visible. I will be going through and reviewing those and making sure all the questions are keyed correctly so that everyone gets the grade that they've earned. And I should be making those available a little bit later today. Um, that's my plan. It's later today is the plan. If anything slows me down, I'll let you guys know on, adjusted timeline. But I don't anticipate having any issues with that. Now, with that said, we were just talking about gases. We are just talking about gases and, a reaction filling a balloon or something like that. And, sometimes, well, gases are products of chemical reactions. For instance, if you've ever gotten baking soda and vinegar, what do you make with baking soda and vinegar? The correct answer is the coolest third grade science project ever. You make a nice volcano. A volcano, Corazon, you're absolutely right. We are on the same wavelength. I was thinking volcano, and you are absolutely right. And Amira, yes, it does. Now, what is the kind of byproduct or what is the kind of, I guess, explosive of that? Well, it's not really an explosive, but what is the product that kind of expands very rapidly? Well, it's carbon dioxide, CO2. You can't see that. And I kind of coughed a little bit there. But carbon dioxide is the gas that's produced when you react vinegar, also known as acetic acid, and baking soda, also known as sodium bicarbonate. CO2 is produced in that reaction. Now, we're going to get into chemical reactions. I got a private message, and I'm sure that this is not just one person asking, but the private message was by asynchronous. Is there no Zoom or Top Hat questions, just a video to watch? That would be correct. So, are we still going to get the 3 extra points on exam 2? Kaylee, you know what? I have transferred that to my to-do list like 4 days, and I'm going to do it again, and that will be fixed today. I'm going to write 1310, exam 2, 3 points. And I'm sorry, that was a direct message, but you're absolutely, yes, those are going to go down. Um, so you'll see that reflected, and then, yeah, that's before the end of the day. I'll do that one first before I start working on exam 3. So then I can close the books on 2, then I can close the books on 3. Okay, so chemical equations. And chemical equations are a nice, I guess it's almost like a nice picture or a nice summary of a chemical reaction. Now, over the course of this semester, this is what we've done. It's quite a bit. Where are we? We're right about, nope, stop right there. Stop right there. I need the pen tool, Joel. Chemical accounting. That's where we are right now. We've got acids and bases and oxidation reduction. We don't have a huge amount of material left. And if you think about the semester, I mean, we've got, what is it, 3 weeks? On Monday, it will be 2 weeks, I think, until our break for Thanksgiving, and then like 1 week afterwards. So the semester is kind of coming down to a close. We don't have a huge amount of meetings left, but we have enough where we're going to cover chemical accounting, acids and bases, and oxidation reduction. I think that, let me see, let me look at, I'm going to pull up our Canvas page, and I'm just going to look at that myself. Um, this is Chem 1310. Chem 1310. We've got, let's see, today We are in week number 11. We have a total of 16 weeks. So we'll call it like four. And it's not even completely 16 weeks because of the fact that um, our final exam is on December 11th. So, in terms of class periods, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 class weekend or class weekends, class meetings, and then the final. And whenever I say class meetings, I'm referring to Friday, despite it being asynchronous, will be a class meeting. Or you could say, lectures instead. So we've got some material left, but it's not an overwhelming amount. Now, chemical accounting is what we're going to talk about. And in part because chemical accounting, and this is something that's kind of like going to follow us a little bit through the remainder of the semester. So this is like if you're a sports person, we are dribbling the basketball right now. And maybe we'll get into like a bounce pass. We're not dunking, we're not shooting three-pointers. Oxidation reduction, that's three-pointers. And maybe like one half court shot. But right now, what we need to work on and shore up and make sure we're good with is our fundamentals. So previously on Lost, or previously this semester, sorry, anytime I say previously, I always think of a TV show that I've watched, like previously on Lost. And it was a TV show that I used to watch. We talked about physical changes. We also talked about chemical changes. Now, these physical changes, they can be observed in different levels. They can be observed on the macro level, where you're boiling water and that liquid water converts to water vapor. On the micro level, where we have individual water molecules that, well, they're going to kind of link up together. They're going to make a solution. They have, you know, the micro level is where you're looking at one water molecule next to another water molecule, and next to another. Then last but not least, we have our symbolic visual. Now, the symbolic model is something that we haven't really talked about, and that's a big part about what we're going to be doing over the next few weeks. Symbolic is basically how we communicate. So macro is what you see. Micro is why it's happening, what types of interactions are being disrupted, and then symbolic is how we communicate, how we explain what's happening. And just to kind of put a bow on all of these different items, well, in the macro, we've got that glass of water where the water is converting. In the micro scale, I want to draw your attention to this is a water molecule, this is a water molecule, this is a water molecule, and then I'm going to erase this last circle because what I want to highlight here is this right here. That is a hydrogen bond. That is the bond that exists between a pair of water molecules. We've talked about hydrogen bonds a little bit previously, but that is an example of a hydrogen bond. So these water molecules, I'm going to label them A and B. Well, those don't have hydrogen bonds between them because they're kind of disparate. They're far away from one another. Now, last but not least is our symbolic. Well, that L and G. And then this arrow right here is kind of another way of describing that, and chemists describe it, and what they say is yields. Another way to describe it is to say it produces. This is effectively saying this chemical reaction takes place, or this reaction, this step takes place. And so what this is telling us is that we have liquid water yielding gaseous water. So liquid water going to a water vapor. Now, we talked quite a bit about, or we've looked at the periodic table before. And on the periodic table, there's a couple of gases that are your diatomic gases. Nitrogen, oxygen, fluorine, iodine, bromine, chlorine, and last but not least, hydrogen. Now, there are, tons of different great ways to learn your diatomic gases. When I was in high school, though, and this has stuck with me ever since high school, is I remember my chemistry teacher, she drew a picture, and it was kind of like this of a person. There's the mustache because we got to have a mustache. Then here's their eyes. And if you're thinking, wow, this guy's art skills are only getting better, you're right. I've been taking classes. We've got that mustache that's going to extend to make a full-blown beard, and then that's where we pick up the rest of the face. We've got some ears on this person. And then I'm going to give him, I think I might give him Bart Simpson hair. Yeah, this is really completing the whole picture right here. And then we've got again our ear, and then boom. That's a person. It's a person. We need to know this person. And when we know who this person is, then we know who all our what all our diatomic gases are. And this person's name is H. Braun Cliff. H. Broncliffe. H. Broncliffe is like a super respected person, as is evidenced by their like intense look on their face and their goatee. You know, I think I was too old for Ed, and Eddie, but I've seen it. I'm familiar with it enough that I think I kind of did draw that. But I, I would say that that is just like one of the great coincidences in human history. So this is H. Broncliffe. And that's their name because what you can do, this is a nice little mnemonic. H, hydrogen. Br, bromine. Oxygen, or O, oxygen. N, nitrogen. Cl, chlorine. Last two are iodine for I, and F for fluorine. Now, an alternative is you just draw the structures, you just draw this little, you know, this box around hydrogen, and then you draw this around, or this basically like a seven around nitrogen, oxygen, chlorine, bromine, and iodine. Now, these are all diatomic gases, and what that means is that they are best, or they love to basically pair up with themselves. So hydrogen, H2, bromine, Br2. These are going to, in their kind of natural state, they're going to pair up with one another. So all of the elements that make up the name H. Broncliffe, those are diatomic gases. Now, that's kind of their like base state. So that's why if you talk about oxygen, well, you're typically talking about O2. Okay. These are all important because these are all commonly going to be used as reactants or products in chemical reactions. Now, here what we've got is carbon, carbon in O2. Okay, now if we look at this picture on the left, you might be thinking, oh, okay, that must be, or you might look at that and say, okay, well, that must be some sort of, I don't know, like a block of charcoal or something, and that is made up of carbon and O2. Got it. Not quite. So that block right there is carbon. If you think about and I don't have one in front of me, but if you have a pencil, you've got graphite that marks on your pieces of paper or your piece of paper. That graphite is a carbon-rich compound. It's basically just a bunch of carbons. Um, and then there's this other compound. Has anyone ever heard of graphene? Graphene is this substance that's really pretty cool because it's super light, but it's like super light, but it's strong. And so it's kind of like you wouldn't expect those two things to go hand in hand. But graphene is something that is super light and super strong. And so at any rate, what we've got in this picture here is that's a block of carbon. And then outside of this, just think about this as like, oh, this is someone's, lab benchtop or something. Well, there's oxygen in the atmosphere. So there's oxygen present there that that molecule can react, or that block can react with. Now I'm going to click this link. It's going to pop up. No, I'm not. Video. Bring me a web browser. Don't open Edge. Okay, good. It didn't. I'm going to bring this over and then I'm going to share, change my share. Oh, freeze, freeze, not so fast. There we go. We've got our charcoal, and that charcoal is basically just carbon. That consists of mostly carbon and is typically obtained from wood by pyrolysis. Pyrolysis, what do you think that is? Any thoughts? What's pyro? That's what, like, I remember when I was in like middle school, everyone was like, I'm a pyromaniac because Beavis and Butthead was a popular show whenever I was up in like fifth and sixth grade. Absolutely. So pyrolysis is basically breaking or cutting with fire. So that's how charcoal can be kind of extracted and picked up. We're going to watch what happens whenever somebody basically just blows a little bit of oxygen to speed up the burning of this charcoal. Yeah, it burns. It burns pretty quickly. And that carbon block plus O2, well, it's going to produce none other than carbon dioxide. I'm going to go back to my original share here, which was the PowerPoint. That's the one. Now, what we've got there, so that's basically a reaction taking place. Now, the gas or the O2 is a gas and the carbon is a solid. CO2 is also a gas. Now, here what we've got is one of the other things that we talked about so far this semester, and that is conservation of mass. Here we have a chemical reaction where we have our separate reactants here and here. When you combine them, before they weigh 173.64 grams, and then whenever you combine them, they combine to weigh 173.64. In that case, well, none of the products that were generated in this reaction were a gas. So the mass did not depreciate or decrease. If a gas is produced in a chemical reaction, which is what you see here, whenever mercuric oxide is burned, well, 92.61 of those 100 grams are mercury, and the remaining 7.39 grams are oxygen or O2. So when you think about chemical accounting and chemical reactions, these are all things that we've got to keep in mind. Especially when you look at something like this. This is an example that I think is pretty simple to keep straight. We've got reactant A and B that produces our product, C. Okay. Then everything that's accounted for on the left-hand side, we've got one carbon and two oxygens. On the right-hand side, where our products are, we've got one carbon and two oxygens. That's like one of the most pivotal parts of understanding chemical reactions. Your reactants, everything that's on the reactant side of the reaction is going to be carried over to what's on the product side of the reaction. Okay. Now, here's our visual for our volcano. Now, okay. Does anyone want to see the volcano? And I'll just give you a little bit of a spoiler. It's maybe not going to be the most exciting. And okay. The people have spoken. I will show the volcano. Okay, I respect that. I respect that. But then you know what else? I'm also okay, so I'm gonna put this volcano on. Okay, so we've got vinegar. Acetic acid is what vinegar is also known as. Caitlin, I kind of wish that you hadn't done that just because the volcano that you just shared as an emoji might be a little bit more exciting than the volcano that we're about to watch. But here we go. Boom. Boom. Live it up. I know. I know. I know. Like on a scale of amazing to super amazing, it's definitely in the top, like, okay, fine, you're not wrong. Okay. Okay. Christian, can you do that with a bathtub? Christian, you are venturing into the realm of stuff that my kids watch on YouTube, where it's Corazon. I like what you think. Well, let me try to put something together. It's not going to be the whole thing, but at any rate, um, yeah, Christian, that's exactly what my kids watch on YouTube, where they're like, "Oh, this YouTuber got something and they put it in their bathtub and then it bubbled and it filled the bathroom and then it filled the bedroom and then it filled the house and so they had to sell the house." And I'm like, "Dang." And then I look and the video has like 13 million views. So that's effectively what's happening here. In the picture on the right, what we've got is where you do the exact same thing, but the gas gets captured. The gas gets captured in a balloon. And that balloon, well, what's in there? Basically nothing but carbon dioxide. Now, the point of this on the right-hand side is to show, well, if you measure out the mass of the vinegar and you measure out the mass of the baking soda, then you can put those in a bottle, capture the gas with the balloon, and you're conserving everything. You're keeping everything trapped. Would that expand even more since there's more pressure? Amira, that's a great question. And to answer that, it would really depend on how much vinegar and how much baking soda you put in there. If you add, you know, yeah, so it really depends. In addition to that, like the size of the balloon. If that balloon, if you get like a small balloon, it's only going to inflate so much, then it would pop. So that would be dramatic. But if you get one of those awesome balloons that you can get at HEB, the ones on you put them on the rubber band and you punch them back and forth, those things can expand for days. And so that would you probably wouldn't be able to get one of those to pop, especially if the bottle you were working with was something like this right here. Just because you'd have those sorts of limitations. Now, when we're talking about balancing or when we're talking about chemical reactions and chemical equations, we always want to talk about balancing them because when we balance them, then the mass of the reactants and the products are conserved. If you look at the top reaction up here, we've got H2O going to H2 and O2. Great. That's water breaking down into hydrogen gas and oxygen gas. Now, the question is this balanced? And we've already got a check mark of no, it's not balanced. Why is it not balanced? What is missing? And what about this is unbalanced? Spoiler, it's one of the elements. Which element is not balanced? Oxygen. Perfect. Okay. Now, to balance that, well, what's done is you put a 2 coefficient in front of the water, but then you've got this instance where you've also got to put a 2 in front of the H2. Now, I always like to, whenever I think about a chemical reaction, I like to kind of draw out the components. It's helpful for me because then I can say, well, what's going on? If I'm going to draw a line down the middle of my slide, reactant, I'm going to say reactant and then products. You know what? I'll change it to reactants. Okay, so we looked at the chemical reaction. We had H2O and H2 and O2. Now, for the sake of, I guess, simplicity, I'll just draw O2 like that. It kind of looks like our old friend H. Broncliffe. Okay, but I'll erase that now. H. Broncliffe with like an eyebrow between their nose or with glasses that aren't glasses. Now, what we've got here, and I'm going to switch color of the pen so that I can highlight this a little bit better. I'm going to go with green. We got a hydrogen and a hydrogen. Okay. That addresses this and this. So check. Hydrogen's done. Now, for our oxygens, on the other hand, well, H2O only has a single oxygen. So if we underline the oxygen over here, well, then oxygen, no dice. Okay, so how do we adjust for that? Or how can we get this reaction to take place? Well, the only way that we can get this reaction to take place is if we have another water molecule. Because that's the only reactant that we're given. And so now what we have is we do have two oxygens. So now we can say, okay, great. The oxygens are accounted for. But that leaves us with hydrogen and hydrogen. Well, the only products that are described are hydrogen. So what we could do anytime we look at a chemical reaction, in order to take something that's unbalanced and make it balanced, the only thing that we can really do is change the number that comes before that formula, because that indicates how many of them there are. So with these leftover hydrogens, we'll just add another H2 molecule. So our second H2 that's also done. So if we kind of go back and basically check each of the elements, hydrogen, 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 hydrogen. Okay, 1, 2, 3, 4. 4 hydrogens are accounted for. Great. And we write that as 2H2. Next up, we've got our oxygens. Well, one oxygen, another oxygen. O2. Done. So effectively, what we have is H2O, 2, goes to 2H2 plus O2. Now, how did we do that? Well, the way that I always kind of like to think about it is we took the molecule H2O and we basically just blew it up. We said, we only want to work with hydrogens and oxygens. So we've kind of taken, I'm going to draw my molecule on the, or I'm going to change what I've got on the left-hand side. And I'm just going to say, well, I got hydrogen, 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 oxygen, oxygen. Now, is there a reason for how I drew that? No. I'm just trying to indicate and to show you the atoms that are there with 2 water molecules. So I basically just broke all of those bonds that I drew between my different atoms, and I just drew the atoms up there. H2, O2, done. Now, you can do the same sort of thing here. C plus O2 yields carbon monoxide, CO. Oh man, this is a little bit of a wrinkle because we've got O2. That's subscript. That's a subscript, but then if we look at our product, CO, neither the carbon nor the oxygen has a subscript. Is that a problem? It's not. Because all that we need to do is manipulate or change the coefficients to get the same number of carbons and oxygens on the left-hand side as on the right-hand side. So again, just kind of blow it up. We've got COO, and we're making CO. Okay, so that's done, but that leaves us with this oxygen. How do we address that? Well, we add another C, which is why we ended up with that 2C in front there. And then we end up with, okay, well, here's my other CO. So I think that it's always helpful to almost, whatever you're given, if it's O2, if it's O6, if it's C5, just kind of blow it up, write the individual atoms, and then say, okay, do I know where all these atoms are coming from? Yes, I do. Where are they going? Well, they're going to this one product. So that's yeah, that's basically the principle behind um, balancing a chemical reaction. They get a little bit more complicated. They can definitely get more complicated, but that's kind of the heart of it all. Now, I want to make sure that I covered everything that I wanted to. Yeah, that was it. We'll do this balancing chemical equations tool for just a little bit, and then I'm gonna say, have a great day. Have a good Wednesday. Go outside, enjoy a walk, get a coffee if you're a coffee drinker. If you're not a coffee drinker, you can or don't have to. So this equation right here shows us, well, we've got a simple reaction, N2 and H2. Now I'm going to increase the number of N2s. That's our two blue balls there. And then H2, two white balls. So we have those, we've got one of each of those. Now, how are we going to make, let's say, three NH3s? Well, in order to do that, we've got to up the number of N2s because right now we've got one N2 and we've got one H2. So if we up this, now we've got four N2s and we've got three nitrogens on our product side. Okay, so that's going to present a problem. And this is one of the things that people go through when they're balancing chemical reactions, is there's almost like a back and forth, like make a change and then see how it works out. So if I were to, let's say, so I'm going to, what I'm trying to balance first, actually, let me go ahead. Let me erase all this. What this chemical reaction is telling me is that N2 and H2 react together to form NH3. Now, I can see here that I have two nitrogens. So how many NH3 do I have to have as a minimum amount of products? I've got to have two, because if I have two, then my numbers of nitrogens are balanced. So I recognize that from the start because the process that I went through was I said balance atoms or elements other than, and this is kind of a good rule to follow, H and O. So hydrogen and oxygen. Save those for later. Okay. And then what I'm going to do is I'm going to say, okay, well, let's see. Are my nitrogens balanced? I've got two nitrogens and then I've got two nitrogens. So now that I've played with that coefficient, I'll say N balanced. Okay, so I feel good about that. Does anyone have any questions about what I've done so far? Okay. And any type of question pops up, just let me know. So we've got my nitrogens balanced because what I wanted to do was I wanted to make sure that the number of non-hydrogen or oxygen were equal on both sides of the equation. And that's what I've got so far. Okay, so now then what we have to do is basically for this one, our next step is going to be to balance atoms, or well, H and O atoms. Balance those two, hydrogen and oxygen. Okay. Now we don't have any oxygens to balance, so I don't have to worry about that. But I can balance my hydrogens. Well, on the reactant side, right now I have 0. On my product side, I've got 6. I know that I have 6 because each NH3 gives me 1, 2, 3, 4, 5, 6. So 6 hydrogens. I've got 6 hydrogens, so, well, there's 2 hydrogens. 2 more, so that brings me 4. Dunzo. Not only is it done, but look at that smiley face that I earned. Booyah. Actually, you know what I'm going to do? I'm going to make that. You guys tell me if you recognize this person at all in just a second. Look at that. It was H. Broncliffe in disguise the whole time. By getting this question right, I revealed H. Broncliffe. It's kind of like a Scooby-Doo. I would H. Broncliffe would have gotten away with it if it weren't for these meddling kids. I being that meddling kid. Okay, so this is essentially what's taking place here. What we've got to do is, you know, I think that the simplest thing to do is to put in the reactants using a tool like this and say, okay, well, I know that I'm going to make at least one NH3. So in order to do that, I have at least one N2 and at least one H2. Okay. Now I'm going to balance my non-hydrogen and oxygen atoms. Well, how do I do that? Well, with N2, then I have to up it to two NH3s. Now with H2, well, I've got to up that. By having two NH3s, I have six hydrogens. So I've got to have three NH2s. Now, another way to look at this is, let's see, can I do it? Yeah, there we go. Now it looks like H. Broncliffe is shocked. Let's see. I'm going to clear this out. Reactants. Oh. Okay, well, I was going to show you something, but I decided not to. I can't. I have a limitation there. But this is like your golden ratio. 1 N2 to 3 H2s. And that gives you 2 NH3s. Okay, everyone. That's where I'm going to call it. I am going to go ahead and stop my share. I'm going to also stop my recording.